Hello, everybody. Um, Good. So I hope you are all okay. Sorry, I will upload this video a bit late this time, but yeah, given the circumstances, I think it's not a big deal. Okay. So, well, this time we will speak about geostrophic flow. Okay. Um, that is, let me put this like that, geostrophic flow. Okay, better. So yeah, remember the last time we have seen, we have derived the motion, okay, the equations of motion for the atmosphere for a rotating planet. So we present these 5 equations, okay, that describe totally describe all the movements in the atmosphere, okay? But what we are going to do now is we are going to actually apply some simplifications. And we will see that simplifications of these equations are indeed describing the large scale motion of the atmosphere very well. So this is the outline of this lecture. We are gonna let me get this laser pointer. Yeah. So we are going to see the geostrophic flow, and then I'm going to introduce some theorem called the Taylor-Proudman theorem. Okay, and then finally we will see something called the thermal wind equation. Okay, that is as well. It's a very good approximation. It's a very good approximated description of a large scale flow in the atmosphere. So let's start just by looking at a map. Okay, so this is the 500 millibar surface wind map where there is the geopotential height field plotted. So you see these iso-ipses here. These lines are lines of constant geopotential height. And then we also, so this is for June 21st of June 2003 in the on the northern hemisphere. Okay, so well, and it's around, it's at mid latitudes. Okay, so this is a typical picture of a different weather systems. So you see here we have some low pressure systems playing around in here, and then here farther in the subtropics we have some areas with a high pressure. You see here we have actually Florida. This is the Caribbean Sea. Okay, so this is actually a plot over the United States. And what we see that here superposed to this plot, we have these barbs. Okay, these are actually showing, these actually show the wind. Okay, so these actually points, so where these barbs are pointing, they show the direction of the wind. And then these perpendicular lines actually show the strength of this wind. Okay, and what we see is that, okay, here in the subtropics, okay, so well, subtropics and basically over the tropics, you see this is the latitude 20 degrees. You see that a bit, well, the winds are all over the place. Okay, they don't follow the isolines, they don't follow any particular direction. But as we go farther up north, we go close to the mid latitudes, we see that actually the wind align very good actually with these isolines of geopotential height. Okay, and this is actually what it's called, the geostrophic wind. Okay, and we will see how is the definition of the geostrophic wind. But basically, the geostrophic wind is this wind actually that follows the iso-ipses of geopotential height to high approximation. Another thing we can see, and we will see it more, that you see, for example, where in the places where the meridional gradient or the gradient of geopotential height is larger. So basically, the iso-ipses of constant geopotential height are packed together. We see that the wind is stronger. You see that there is a more these perpendicular lines to the barb. Okay, and actually, where they are not so close together. Okay, the wind is just weaker. Okay? So we already have seen that actually this already tells us something about the relationship between the geopotential high and the wind. Okay? Probably it will involve gradients of geopotential high. So now let's derive an expression for the geostrophic flow, and we will start just by using the momentum, the horizontal momentum equations. Remember that in the vertical, we basically assume that the atmosphere is in a hydrostatic balance, which is an excellent approximation. So these actually are just the momentum equations on the horizontal, so in the x and the y axis, or the zonal and meridional direction, if you want. And see that we use now pressure surfaces. So we use the pressure as our vertical coordinate. And so then let's say our horizontal pressure gradient forces, if you want to call it like that, okay, are expressed in terms of geopotential. Okay. Let's say our horizontal forces are expressed in terms of gradients of geopotential in surfaces of pressure, of constant pressure. Okay, we can do something now, and we have neglect friction. Okay, we are higher up now in the atmosphere. Okay, we are in what is called the free atmosphere, and we can also, with a very good approximation, neglect the effects of friction. So we can do something that it's called a scale analysis. Okay, we can try to give an order of magnitude for the different terms of the momentum equation. So let's expand this left-hand side of the momentum equation in here. So this is just partial v partial t, the advection component of the total derivative, and then the Coriolis force. And we can just, let's put just some order of magnitudes in here, okay? So this is basically what is the magnitudes of this partial v partial t. Well, it is velocity and it's time, so it is the scale magnitude is u over t. Okay, here what we have is we have a spatial derivative, okay, a gradient, so it's a spatial derivative of velocity multiplied by another velocity. So we have basically u squared over L, right? Because a partial, it would be partial v partial x, partial v partial y, okay? So basically in the denominator we have distance, okay? And here again we have this is basically the cross product of vector k, so it's unidimensional. It has no dimension. It's or their dimension is 1 actually, and v multiplied by the Coriolis parameter. So the magnitude, okay, the scale magnitude would be something like fu. So now we just have to give typical magnitudes of these variables, okay, at mid-latitudes. And just because of our observations, we know that typical magnitude of a zonal velocity is something like 10 meters per second. Okay? This is just an order of magnitude. It's the order of magnitude. It's about, sometimes it would be 50 meters per second, sometimes it will be 5 meters per second, but it's the order of 10. Okay? Scale. What is the scale of a typical synoptic? Okay, because we are interested in the synoptic scale, in the movements that are occurring at mid-latitudes, typical size of a weather system, okay, of a high-level pressure system or a low pressure system. Let's say it's something around 1 million meters, so something around 1,000 kilometers. That is a typical scale. And what are the typical time, okay, in which these systems evolve? Well, let's say it's something about 100,000 seconds, so it's the order of 1-2 days. Okay, typical time of evolution of a weather system. Though by taking these magnitudes, okay, we can just see that actually these two terms have the same order of magnitude, and it has the magnitude, okay, both are accelerations, of course, because all of that are accelerations, and is the order of 10 to the power of -4 meters over second squared. But actually, if now we put the order of magnitude of this term in here, okay, the Coriolis force, the Coriolis acceleration, we see that the typical at 45 degrees, let's say in mid-latitudes, the Coriolis parameter is the order of 10 to the power of -4. Velocities is the order of 10 we have set. So then this says that this term in here is the order of 10 to the power of -3. Okay, so it's one order of magnitude bigger than these two terms. So this term, okay, is much bigger than these acceleration terms in here. Okay, and we will see, okay, also due to our experience by observing the atmosphere, that actually the pressure gradient force or the geopotential gradient has the same order of the Coriolis term. It's the order of 10 to the power of -3. Okay, so both of them are an order of magnitude larger than this advection and these acceleration terms. So this already tells us, okay, that possibly a good approximation, okay, would be actually to just eliminate this term here and get actually a balance between the pressure, the geopotential gradient, and the force due to the geopotential gradient and the Coriolis force. Okay, and this is indeed actually what it's called a geostrophic balance. Okay, so the geostrophic balance is a geostrophic flow. It's the flow that results from a balance between perfect balance between the Coriolis force and the geopotential gradient force. When we know that we can apply this approximation, well, we can actually build, okay, some parameter that it's actually called the Rossby number, and this is a very important parameter. Okay, this is basically the ratio between these acceleration terms and this Coriolis parameter. Okay, so the magnitudes, you can see if you just get this u squared over L and you divide by FU, you get this expression in here. Okay, so when this parameter is very small, so it's the order of 0.1, this means it is telling you that actually the Coriolis force dominates over these acceleration terms, so possibly the flow is going to be close to geostrophic balance. Okay, the flow indeed is never just perfectly geostrophic. Okay, and we will see more on that. Okay, so for example, in this plot we've seen before, we see, for example, if you go close to the pressure, okay, to this minimum low pressure system, you see actually that the flow is not perfectly following the constant lines of geopotential, but it has some tendency to actually converge into the center of the low pressure system. Okay, this is what it's called actually the ageostrophic part of the flow. So basically, you can take a flow, the real flow, and divide it by its geostrophic plus its ageostrophic part. But in mid-latitudes, always the geostrophic flow will be much, much larger. And you can actually describe the flow quite good just by supposing that these acceleration terms are 0. So, okay, we've seen actually that for small Rossby numbers, okay, the large scale motion in the free atmosphere and the ocean also as well, but in this course we will not cover the ocean, but just for you to know that the same equations can also are useful to describe the ocean fluid motion. Okay, basically implies that the Coriolis term dominates the acceleration term, so we get a balance between these two terms, Coriolis force and geopotential gradient force. Okay, now we can just solve this equation by V, and we obtain an expression for the geostrophic velocity. And we found, so this is the vectorial expression, and then we can just get the components of this, and we found that the velocity, the zonal geostrophic velocity equals to 1 over f, and the spatial derivative, so the partial derivative of geopotential over the meridional direction on a pressure, on a surface of constant pressure, okay? And the same by the meridional velocity, but in that case is proportional to partial phi partial x. So differences on geopotential on the zonal direction. So let's imagine now, okay, let's try to understand that intuitively. So imagine this is these are lines of a geopotential high, okay? This is the equator over here. This is the pole over there, okay? And we have a meridional gradient of geopotential high. So the geopotential high is larger in the tropics just because the temperatures are higher. Remember the hypsometric equation, and are lower over the poles. So we have a pressure, a gradient of geopotential in the meridional direction. So then this expression here, this partial phi partial y, it is positive, okay? And that actually implies, okay, so we have a force, we'll have an acceleration. So a fluid particle is going to start accelerating. But now remember that the Coriolis force, okay, is proportional to the velocity, okay? So as it accelerates, as it increases the velocity of the particle, the Coriolis force also gets bigger, and it tends to turn, remember that it's perpendicular to the velocity, okay, pointing to the right, so it tends to deviate the particle onto the right direction in the northern hemisphere. So the particle is going to start accelerating and bending towards the right until when? Well, until the geostrophic wind is realized, or until the force due to the geopotential gradient equals to the force of the Coriolis force. So this is the balance, okay? This is the pressure gradient force, or the geopotential gradient force, okay? And this is indeed the Coriolis force. And when these are in balance, we got what is called the geostrophic wind that is perpendicular, is parallel to the constant lines of geopotential high. Okay? And this is what we've seen in this plot before in this map. Basically, that the wind is following the lines of constant geopotential high. Now, an important thing to look at, okay, is that indeed this wind, the geostrophic wind, is non-divergent, okay? So there is no convergence, okay? There is no convergence of the wind. So actually, okay, let's look again at this. You see, the wind constantly follows these lines. It doesn't really accumulate, okay? If it would be perfectly geostrophic, it would just follow the lines. And what would happen then? Well, we would never have convergence, so we couldn't have then vertical movement, okay? Because actually, if you imagine, if you have a convergence of wind just by mass continuity, then you have, this have to be compensated by upward motions. This is what happened in the center of a low pressure system. You see that we have a small, a geostrophic component of the wind. So we have a small component that points towards the center of the low pressure system. This is actually, let's say, accumulating mass in the center of the low pressure system. And this is compensated by upward motion, okay? So actually, the upward motion comes from the geostrophic part of the wind, okay? If the wind would just follow, it would just keep spinning around here, okay? It would never evolve, actually, okay? Because indeed, we have, the approximation we have done is to eliminate the tendency of the wind, right? So we just eliminate the partial derivatives over t. We suppose that the flow doesn't evolve. So if the flow would be perfectly geostrophic, we would just see this picture here, and this would be all. That would be all. The wind would just keep spinning and spinning around here. Nothing else would happen. Okay. So you see that the geostrophic component of the wind is very small, but still it's very important because it gives evolution to the weather. Okay. Okay. So we can now define something. I will just define it in here, but we will use it in following classes. Okay. This is just a definition. Is what we can define something that is called the string function. In that case, the geostrophic string function. So basically, is a scalar field, okay, from which you can actually get all the properties of the flow. Okay, remember that the spatial derivative of a potential field, okay, of a scalar field, give us velocities, give us the forces, okay, etc., etc. So this is something similar, okay, is just a scalar field that we call a string function, right? And we define it in such a way that the partial derivative over the space give us back the velocities, okay, the geostrophic velocities in that case, and actually, yeah. And how we define it? Well, just by looking at these equations in here, this equation in here, we see that such the function that a functioning to which this partial derivative gives us the geopotential, the velocity, the geostrophic velocity is just this. So basically, the string function is the geopotential field scaled by the Coriolis parameter. Okay. Just keep that in mind. Okay, that if I give you the string function, from it you can get the velocity field and you can get the geopotential. So you can get from that basically all the quantities that describe the fluid motion. Okay, for now let's forget about that for now. Okay, we will see it again later on. Let's just try to give an order of magnitude of this geostrophic wind. And also, it will help you to get a sense of the relationship between the geopotential high and actually the wind. So this is a typical map, okay? This is a typical map of the northern hemisphere geopotential high. This, in that case, is January 2003. And this is the geopotential high at a pressure surface of 500 millimeters, okay? And so this is actually, you can look at that, okay? And this is actually, you have to, this is expressed in centennials, okay? But okay, doesn't matter too much now. What is important is that we can see from this map that the surface height, okay, in the tropics is around 5.88 kilometers. And close to the poles, it is 498 centennials, so it's around 4.98 kilometers. So we see that there is a gradient of geopotential height. We see that actually is the slope of geopotential is so the geopotential high is sloping downwards from the tropics to the poles due to the temperature differences. Okay, so now we can just get a number for the zonal wind. So we have seen from this expression that is okay. So the zonal wind is the partial phi partial y. So okay, in a discrete form, this is just if we plug in here. Remember that geopotential high is just geopotential divided by G, okay? So change of geopotential equals G multiplied by the difference of height, okay? This is basically the meridional distance that we say that is about 5 million meters, so 5,000 kilometers. Coriolis parameter, we get a typical mid-latitude Coriolis parameter where we want to actually derive the magnitude of this flow, and we put all these numbers together. You see there is approx 1,000 meter difference, and this gets us a magnitude of 19.62 meters per second. That is actually quite close of a middle typical velocity at this 500 millibars. Okay, so you can see now that just for having an instantaneous picture of the geopotential high, you can see the direction of the flow. So you see that at mid-latitudes, the flow, because it's close to geostrophic, will closely follow geopotential flow. So we see actually here we have southward advection here. Then we have here poleward advection now. So probably this is going to carry cold air. You see equatorward. Then we have, and this goes up again. And also we can just by checking the meridional derivative of these isolines of geopotential high, we can infer the velocity. Okay, let's now finish for now to talk about this geostrophic wind. And let's try to remember actually this video I show you on YouTube from these tank experiments, where we've seen actually what are the effects of rotation over a fluid. If you can remember, in the experiment we had some tank, okay, that when it was not spinning, if you put just some ink, okay, just to see, that can help you to track the movement of, and we just perturb a bit the movement, you see actually that it mixes. Okay, we had something like this picture. There was a constant movement, chaotic movement of particles of fluid, okay, and there was no much structures that we can see. But then, if you remember, we've seen that when we start spinning the tank, the fluid got some vertical rigidity, okay, and it start actually moving in a coherent way. Okay, remember, then we can start seeing patterns on the tank fluid that look quite similar to the real atmosphere. And this is actually, we have just seen that from this experiment, but this, it is described in what it's called this Taylor-Proudman theorem, that basically states something like that, that if the fluid is homogeneous, okay, so we have a uniform density, then the geostrophic flow is two-dimensional and does not vary in the direction of the rotation of the vector, of the angular velocity vector. In other words, the flow is two-dimensional, and this is indeed a very strong constraint due to the Earth rotation. Okay, so basically what it says, okay, is that what it comes to say is that if we take the vertical derivatives of the geostrophic flow, then, and we use hydrostatic balance, we've seen that the geostrophic flow doesn't change on altitude. So the partial U over partial Z does not vary in the vertical direction, okay? So what it shows basically is that if we have a column, okay, we have a column of fluid, there is no shear, okay? The velocity, the geostrophic velocity at the bottom of our column is going to be the same of the vertical velocity, sorry, of the horizontal velocity at the top of our column. So the fluid will move in a coherent way. Okay. We'll see that this is only possible if the density only changes with pressure. if the density of a fluid changes with temperature, as it is the real case, then this is it's not true anymore, okay? So, well, this is just a formal derivation, okay? This is the equation of motion, where now we put the three components of it, okay? This is just a way to express the acceleration due to the gravity, plus remember the centrifugal force, okay, Coriolis force, friction, pressure gradient force, and acceleration. Now we take the Coriolis, the geostrophic approximation. So what does it mean? It means that this term, acceleration term, equals to 0. In the geostrophic approximation, we neglect acceleration, okay? And we also neglect a friction because we suppose that we are in the free atmosphere, so we are far from the surface. And then we can just see that if we take the rotational of this expression in here, okay, it gives us this expression in here. Basically, what it tells this expression is that the divergence, okay, of the geostrophic flow on the direction of omega, okay, of the angular velocity equals 0 if the density is only a function of p, okay? I know that is just following what I tell you, it's very difficult to see. So you should check that, okay? You can just check that. You can just play a bit about it, okay? And you will see that by just assuming geostrophic approximation, it's assuming that the geostrophic approximation is true, and by taking the rotational of this expression of the geostrophic approximation, okay, we get this expression in here. That just this expression in here, it just tells us that the partial u partial z equals 0, okay, because this is just the projection of the gradient operator over the angular momentum, the angular velocity vector that we know that it's on the direction of z by definition. So then this expression is totally equivalent to this expression in here. So this is a formal mathematical expression of this of the Taylor-Proudman theorem, and actually is just a mathematical demonstration that for a geostrophic flow in which the density only changes with pressure, okay, the vertical structure of the fluid have strong rigidity, okay. So is that basic, okay? So if we would be in a place like in our tank of water, because of course in a tank of water, because the fluid depth is very small, you can, it's very small, okay, then the density, okay, it's not about it's very small, so we had the fluid that had a constant temperature, an homogeneous temperature, right? So then, because of the theories, this theorem just tells us that in that case, okay, the movement would be coherent on the vertical. Okay, so this is a movement that it's called a fluid movement, a fluid structure that is called barotropic. Okay, and here is what it shows. Okay, so imagine we have this column of fluid. Okay, so in the direction of our angular velocity, the fluid has rigidity. The same, if the fluid, imagine it's spinning clockwise, it would spin exactly clockwise, following exactly the same trajectory and the same velocity, the same magnitude of velocity higher up on this column. However, this is not really true in the real world, right? So this is a typical picture. So this is just a meridional hood, okay, of a section of the atmosphere. You see, this is latitude, this is pressure in here, okay. So we go for higher up on the troposphere to the surface, and this is just shows the magnitude of the zonal average zonal winds, okay. So the winds that flow on the x direction, and we see that the real structure. So we have easterly winds, winds flowing towards the west on the tropics. And then at mid-latitudes, we see that indeed we have these two strong jets, okay? And we see that the flow actually increase its speed with altitude. You see, the flow velocity peaks at around 200 millibars, and then it keeps decreasing as it goes close to the surface. And this is due, and this actually it contradicts the theory, well, it doesn't contradict, but this is not, you see, if we actually think on the Taylor-Browman theorem, this is just telling us that totally doesn't look like that the fluid is coherent on the vertical. It's just tell us that the density, it not only depends on the pressure, okay? Because indeed, it also depends in temperature, okay? We know that in the atmosphere, in general, the density of the air depends on pressure. As we go higher up, the pressure decreases, but also depends on the temperature, okay? So let's get this plotting here, and let's derive something that is called the thermal wind equation, okay? That is just a description of this change of wind intensity with altitude. So imagine this is just our vertical direction, okay? This is our meridional direction. Here we have the equator, okay, on the right, and now we have here the poles on the poles here that are colder. And remember actually that just by the hypsometric equation, okay, remember that actually the change of geopotential height, the change of Z, if you want, geopotential height, geopotential height, we just divide by G, okay, is proportional to temperature. So, okay, that means basically that because the equator is warmer, okay, the lines of constant pressure, okay, are more are not close, so are more separated between each other than they are on the cold poles, where the lines of geopotential, okay, are more packed together. Okay, remember that the thickness of a layer of atmosphere is proportional to the temperature of this layer. Okay, so in the poles, because the temperature is colder, the thickness, okay, is smaller. So between two surfaces of the same pressure, so the pressure change faster, if you want, with height. Okay, and this has a clearly geometric. Just clearly you can see that if here we have more packed surfaces of constant pressure than in the equator, then as we go up in the atmosphere, this slope, the slope of these pressure surfaces is going to increase. And then the horizontal pressure gradient is just going to become larger and larger as we go higher up in the atmosphere. Okay, this is very important that you understand that well. Okay, so think a bit about it. Think a bit why these actually the slopes of surfaces of constant pressure increase as you go up. Okay, as you go farther up in the atmosphere. And if you have some problem understanding that, just tell me, and I will try to explain it again. Okay, I might put some other examples or so, because this is important to understand. Okay, so what we have that the pressure gradient forces, okay, are larger higher up in the atmosphere than they are close to the surface, and this have immediate implication that the velocity higher up, the geostrophic velocity, that you know is proportional to the pressure gradient force or to the geopotential gradient force, is just larger. Okay, so then we have that this profile of velocity. Okay, we have that the partial derivative of u over z is positive. Okay, So this is just an intuitive way. It's just an intuitive, it's just to get an intuitive understanding of the thermal wind equation. Let's try to get an expression of the velocity change respect to altitude. Okay, and what we'll do is we'll just start by expressing the geostrophic wind, okay, as we know, okay, and this is the typical expression. Let's just do that for the zonal component, because then it's very easy to derive it from the meridional component. So we have that the zonal geostrophic wind is 1 over F, partial phi, partial Y in a constant pressure surface, okay. If now we derive that, so we derive that over vertical direction, that is what we want to get. We want to get this. This is indeed the thermal wind, okay, how the geostrophic wind change altitude or with pressure. We get this expression, okay, so we derive in each side of here. And now just by changing the order of differentiation, okay, we can, and by using the hydrostatic equation, so we change this is going to be partial phi, partial p. We just use the hydrostatic equation, and now we get an expression that relates the change of geostrophic wind respect to altitude with the meridional temperature gradient. So we see that the rate of change of the geostrophic wind with altitude is proportional to the meridional gradients of temperature, okay? And this is for the zonal component, and this is for the meridional component, exactly the same, but in that case, the change of the meridional component of the geostrophic wind is proportional to the zonal gradients of temperature. So then basically what we see is that the vertical shear of the westerly geostrophic wind depends on the north-south gradient of temperature, right? And now we can put these two things together, okay? So we've seen that the rotation imposes a big constraint to the movement. So the movement is not chaotic because the planet is rotating and it imposes rigidity. But this rigidity is counteracted, okay, by the fact that the density, it's not only function of pressure, but also function of temperature. And in our planet, we have differential heating, right? So the equator, it's warmer than the poles, okay? So we have two ingredients, okay? Two big constraints to the large scale flow. We have the constraint due to the planet rotation and meridional temperature gradients. So we can think of the large scale flow as columns, okay, of air that has some rigidity due to the fact that the planet in rotation rotated but tilted, because we have that the velocity close to the surface is smaller than farther above because we have differential heating, meridional differential heating, okay? So now we just have seen actually two very important constraints to the flow, to the large scale flow motion, that are rotation and differential heating, okay? And we have seen that we can put these two things together and imagine the flow that is moving as columns, indeed. So it has some rigidity. Our atmosphere is not totally chaotic, okay? But it's like not perfect like we've seen in the tank, but just tilted, okay? Because we have stronger velocities on higher above than close to the sun. So we have some shear, okay? So we have columns of air moving around with shear, okay? This is, you can say that at first approximation, this is how the large scale motion behaves. This is just a generalization, okay, of this Taylor-Proudman theorem, okay, and it's just a way to put to mathematically express this into this thing I just tell, okay, that these two strong constraints, these two facts, rotation plus meridional temperature gradient, impose two strong constraints to the large scale atmospheric motion. Okay, so you can check it. Okay, you can just check this mathematical derivation. Think a bit about it. Okay, it is not the derivation. I am not gonna ask the details of this derivation. Okay, I'm not interested in you to exactly be able to derive it step by step, just to understand the general concepts. Okay, so look at this expression here, try to think a bit about it. Okay, and remember, of course, the pictorial mathematics. I hope all of you remember it indeed, because that's quite important to understand what these equations mean. Okay, so that is all for today. I will next class I will derive other approximations, okay, of the equations of motion to describe other kind of movements. But I think this is an important chapter, okay? So be sure to look over it. Also, you can find more detailed explanations are in, for example, in Holton in the book, or well, all the other books I actually suggest you in the bibliography. Okay, you can also write me an email if you have some doubt. We can even have some gypsy talks one by one if it's needed. So yeah, okay, thank you very much and have a nice day. I see you next Monday.